So our last video in Mod 14, we have an exponential growth or decay formula, which looks like this. And this is really, we're just using different variables. It's the exact same as A equals P e to the RT power. A equals P e to the RT power. And all we're doing is we're using y to be our A value, y sub 0 or y naught is our initial value P. And that's the only thing that's different. We do start talking about things growing versus decaying. And what we need to remember is if we have something decaying, that decay rate will be negative. So we would need to put a negative value in our problem. But outside of that, everything's exactly the same. But I'm going to use the different notation. It's a little more science-based, because you might see some stuff like that in future classes, different classes. So here we have the number of organisms in a certain population. And again, if you remember in the last video, I said population grows exponentially. It is predicted to decrease. So population decrease, that's going to mean we use a negative rate using continuous exponential decay model. We know what our rate is. It's 12% per hour. And if the sample culture has an initial population, that's my y sub 0, of 987 organisms, we want to find the end population, the amount present after 5 hours have passed. So we know what our T will be. So I'll just list what we know here. We know that our rate R is going to be negative 0.12. So decay, we use negative, and then that 12%, we need to move the decimal left 2 places. We know what the initial population, or y sub 0, is 987. And we know how much time will be elapsing. It will be 5 hours. So, setting this up, y is what we don't know, the end amount, is going to equal y sub 0, 987, e to the negative RT. So we've got negative 0.12 times 5. And at this point, you just have to plug that right into your calculator. And you end up with y equals approximately 541.7. Or rather, we will have 541.7 organisms. So that 0.7 organism might still be growing. All right, example 14. We have a mass of radioactive substance following a continuous exponential decay model. So again, we're using that formula, y equals y sub 0 e to the RT. And because it says decay, we know that R is negative. We have a decay rate, 6.4% per day, and we want to find the half-life of the substance. So a half-life is how long it takes for the organism to decay to 1/2 of what we initially had in our sample size. So we'll round our answer to the nearest 10th. So I'll start by writing my formula down. Y equals y sub 0 e to the RT. Well, we know what our rate is. R is negative 0.064. We do not know time, and we don't have a principal and an initial amount. But in our last video, we did an example where something doubled. So in this situation, we can do an example where something decays to half. And so when we think about it, if we start and we have that y sub 0 equals 2, then half of that, y, would be 1. And we can use any values we want. I could use 100 and decay that to 50. I'm just trying to pick nice, easy numbers to deal with. So I'll use that as my initial and end amounts. And here when we set this up, I will say that 1 equals 2 e to the negative 0.064 t. And so we are looking for how long. So if we're looking for how long, if we're looking to find the half-life, that means we're solving for t. So isolating the t, I'm going to divide on both sides by 2. I have 1/2 equals e to the negative 0.064 t. To solve this exponential equation, I'll take the natural log of both sides, and taking the natural log of e to the negative 0.064 t. What that does is that allows the ln and the e to go away, and it brings that exponent down. So we end up with the natural log of 1/2 equals negative 0.064 t. Dividing on both sides, the natural log of 1/2 divided by that negative 0.064 equals our t value. If we plug that into our calculator, we get that t is approximately 10.8. So what that tells us is whatever we start with, whatever this radioactive substance is, if I start with 100 grams of it, then after 10.8 days, I will have 50 grams. And then after another 10.8 days, I would have 25 grams. And another 10.8 days, so roughly 33 days, I would have half of that 25, which would be 12.5 grams. So it's decaying by half. Half of it's going away each of those 10.5 days. Excuse me, I said 10.5. So here we have t equals 10.8 days, and that would be our answer. And we know it is days because the rate says per day. Okay, and we have problem 15 here. The size of an insect population at time t in hours obeys this given exponential model. If we are asked to determine the number of insects at time t, that would be plugging in 0 for t. That's our initial amount. So this is going to give us the initial population. And if I do that, I say y equals 500 e to the 0.03 times 0. So 0.03 times 0 is 0, and e to the 0th power is 1. So we end up with 500 insects. And if you look in your problem, that 500 is occurring right where the initial amount would show up. The growth rate. What is the growth rate of the insect population? So the growth rate is 0.03, which is 3%. And we know it is a growth rate because that 0.03 is positive. So if we're asked to solve the problem, when will the insect population reach 800? When means t is what we don't know. So I'm going to set this up. 800 being my end amount equals 500 e to the 0.03 t. I'll divide by 500 on both sides. I have 8/5 equals e to the 0.03 t. I'll take the natural log of both sides. So I've got the natural log of 8/5 and the natural log of e. That's just going to bring that exponent down. And lastly, I would divide. So I've got the natural log of 8/5, all of which is divided by 0.03 is equal to t. In this case, t is approximately 15.67. So that means 15.67. And if we go back and we look at our start of our problem, it says in hours, so 15.67 hours. So if we start with 500 insects in this population and their growth rate is 3% per hour, then we know after 15.67 hours we'll have 800 of these insects. All right, and we have one last problem here. We have a population of 120 fish introduced to a lake, and this fish population grows according to an exponential growth model. There are 288 fish in the lake after 8 years. Let T be the time in years since the initial population is introduced, and let Y be the number of fish at time T. So let's write a formula. Because these fish, this population is growing according to a continuous exponential growth model, we're using our y equals y sub 0 e to the RT. That doesn't really look like it's in the exponent. So in this case, we set this up and we say y equals 120 e to the RT. So 120 is my initial population. My end population is 288. And that occurs after 8 years. So I'll plug in 8 for T. So again, we're solving this problem, this equation, for a variable which is in the exponent. So we're going to divide, natural log, and then divide again. So dividing on both sides by 120, 288 divided by 120 gives me 2.4. E to the 8R, natural log of both sides, the natural log of 2.4, and the natural log of E is going to cancel and the 8R comes down. Divide on both sides by 8, natural log of 2.4 divided by 8 equals R. So what we end up with, that is my rate. So if I want to write my function, I could say y equals 120 e, and then my rate is the natural log of 2.4 divided by 8 t. So if we wanted to know how many fish there are 18 years after the initial population is introduced, we would just plug the 18 years in. And so because that rate, I need it to be precise, I'm keeping my rate in an exact format as opposed to plugging it into my calculator and getting an approximate decimal. So at this point, we would just say that y is 120 e, and the e is raised to the ln 2.4 divided by 8, all of which would be times 18. And if you plug that into your calculator, you'll get approximately 860. So at the end of 18 years, we would assume there were 860 fish in the lake.